Yes, it works. Okay, so thank you for coming. You already saw this picture earlier, so let's just recall what we are dealing with here. So this is the world as we know it now, and with everything that's happened and the relevant bits regarding digital security and the exact algorithms, or let's say techniques maybe, that influence the digital security. Why is digital security so important? We saw just a bit of this picture earlier, but this is a report for 2018 showing that, well, the internet and the communication over internet has become like an everyday thing for us, and that we simply cannot imagine our lives without the internet. In particular, these numbers are very, very big. So the total number of people that do online shopping, it's more than 1.5 billion. How many consumer, how much, okay, how much is the average spending online? And the value of the market is even bigger. So all this needs to be done securely. I have a very nice picture here. So the digital security kind of guards our everyday lives, starting from the security of our bank cards and online shopping, the security of our identity. So think about privacy and the recent issues with Facebook and breaches with LinkedIn, for example, and so on, that show that our privacy is probably not as private as we might think. But what lies behind digital security? Well, one of the most important let's say techniques or tools that are used behind digital security is cryptography. And crypto, as we call it for short, is basically math. So next I'm going to show you what actually cryptography does in digital security, and you will see that you can't even think of other things that are not done without cryptography. So here are our favorite characters. Alice wants to send a message to Bob. Dear Bob, I miss you. So this message goes through the internet. We have no idea what happens, and it gets on the other side to Bob. Now imagine there is the evil party that listens to the conversation. Actually, it's really easy to listen to a wireless conversation. It's not like it's a wire, and you have to cut the wire in order to listen to it. So, for example, if you're sitting in a, I don't know, in a cafe with a wireless connection, and if it's not secure, then it's very easy for someone to listen to the conversation. So what do Alice and Bob want to do? So they don't want their conversation to be heard. They want it to be confidential. So they invent a so-called encryption algorithm. So Alice will put her message through an encryption algorithm. What comes out is a ciphertext. And what the evil party sees is actually some gibberish. It has no meaning to the evil party. This ciphertext comes to the side of Bob, and Bob uses a decryption algorithm to see the message. So how do these algorithms work? Well, first of all, Alice needs some sort of a key, and this key needs to be secret. In principle, the encryption algorithms are not secret. Everybody knows what the encryption algorithms are. For example, everybody knows how AES works or how RSA works. So they're public. What is a secret is the key. So in this case, Alice needs a key AB. Actually, Bob needs the same key. So this is a kind of a symmetric type of encryption. And the point here is that, well, these keys don't come out of nowhere. And if Alice and Bob need to know exactly the same key, they need to meet prior to this communication in order to exchange the keys. But in reality, well, what if I just want to communicate to a server like the one that hosts my favorite, let's say, web shop, let's say Zalando, and so we don't exchange keys before that. We don't meet, right? So this is a problem. Well, Alice and Bob think of another approach. So now Alice and Bob have two keys. Both parties have two keys, and they don't look the same. That's because one is public and the other one is private. And why is this called public? Because we can just publish it in a newspaper and everybody can see it, and this will not compromise the security in any way. What is even better, not only doesn't it compromise the security, but anyone who just takes that key from the newspaper, reads the key, and puts it in their encryption algorithm can send me an encrypted message. So that's what Alice is going to do. So use Bob's public key to encrypt the message, and on the other side, Bob will decrypt using this key. So this is very, very nice. So now this problem has been solved. So this, it's called public key crypto, and it was invented in the 70s, and actually that was the breakthrough of cryptography. And since then, we have all these beautiful things that can be done with it. There is one problem though. Well, this is extremely expensive. So, for example, if I want to send a very long message, encrypting it using public key cryptography will be like, okay, I'm clicking on the website and I can go eat and come back and see what's going on. Like, it's not that much, but I'm a bit exaggerating, but it's a lot of time. It's not good to encrypt the entire traffic, but what we can do is actually use this idea to exchange the key in the previous slide. So now they will have that key, exchange it using this idea, and then use it with algorithms that are much faster. Actually, for symmetric crypto, they are extremely fast. But this is not the only problem that Alice and Bob have. It's not just confidentiality. Recall earlier I said that if I, for example, tell my bank, send this amount of money to another party, and that party or completely different party can change the content of this message, the bank will again receive a message from me, but it will be changed. So integrity of messages is an important thing. Alice and Bob have quite a few problems. So this is one, that they want to make sure nobody changed their messages. But also, Bob wants to be sure that he's talking to Alice. What is this? You may say, like, okay, they do know who they're talking to, right? If I write an email to someone and use their email address, I know that I'm talking to them. But think of it this way. Are you sure that you're actually talking to the Zalando server when you're online? So someone may pretend to be it, show you a very similar page, use an URL that is very similar to the one, so that you don't always check exactly the URL of whom you're talking to. So it is possible. So both parties want to know that, and Alice as well. Another thing. What if at some point Alice sends a message like, I don't know, some very important state matters, and Alice said, like, push that button, Bob. And then Alice says, oh, I didn't say it. Something goes wrong, and then Alice says, no, I didn't say it. But we want to prove that this is the case. So usually for example, in real life, this is real life as well, but without computers, we would first at the beginning sign some contract, and the contract will say some clauses, and then you can't escape from the contract, more or less, something like that. And another important thing that emerges now is the following. So, for example, we now communicate using encryption to some other party. And imagine we are preparing, I don't know, some very secret matter. I'm not going to say examples in this case, but this is of state importance, let's say. And everything is fine. No one can read the messages. But who guarantees that, for example, after 10, 15 years, someone will not have a good algorithm, a quantum computer or something, and go back, save those messages, if the messages have been saved, and find those messages in some files and read them. And some maybe state secrets will be discovered. So this is a realistic thing. Actually, Edward Snowden's revelation showed that the NSA is doing this. They're collecting all the traffic and the one that they think it's important, and they're just storing it somewhere on some servers. Some say that maybe they can decrypt it now, but the crypto community thinks that actually that's not the case, but they are hoping that in some time they will be able to do that. So they then will go back and read all the, I don't know, terrorist plans and so on. So many important things. So one of the things previously, that is not one but several, can be solved using this approach. So here is the evil one, malice. And for example, this is the previous conversation, and it changed the message. So now that it's "Dear Bob, I hate you." You can't really change it like this, let's be honest, but you can maybe scramble it or something. So in order, but Bob has no idea that this has happened. So in order to be sure that this is not the case, this is what happens. Alice uses her private key to sign the message. So she attaches her signature to the message. And now this whole thing, the ciphertext together with the signature, is being transmitted on the other side. So in this case, Bob gets some possibly changed message and some signature, maybe possibly changed signature. And then he uses some sort of an algorithm to check whether indeed this message has been signed with this signature. So this is very similar to what is happening on paper, right? So there are techniques to check whether somebody actually did give this signature, did sign the document. So if this is called verification. So if this fails, then Bob knows that Alice didn't send this message, so that it was being tampered with. So in this case, Bob not only checks that the message is correct, he also makes sure, like this mechanism also provides the guarantee that Bob indeed knows that this was Alice, because she and only she has this private key and nobody else could have done this. So in general, digital signatures are used in many different things in digital security, like many of the protocols that are used today, like HTTPS, for example, uses them. Okay, so this was like a crash course in crypto and what crypto can do, but not actually what the underlying things are. So here I have 4 pictures showing 4 different problems, mathematical problems. Well, the first one, yeah, you might say it's not a mathematical problem, but yeah, I'd say problem in computer science as well. So this would be searching a database. So if this database like has n items, how many times do we need to look up? Well, in the worst case, n times. So it has, yeah, that's the amount of work that we need to do. The second problem is multiplication of a vector and a matrix. Okay, we know how to do this. Even if you use some computer-enhanced program, this is doable and at most quadratic steps. So if we count all the operations here, we will see that that's at most 9. This is fairly easy. It's a bit more difficult than the previous, but it's easy. This one here, this one here, but yeah, it's okay. Is an exempt of the 3-sat problem to represent in a specific form whatever formula, mathematical, what it's called, logical formula, to represent it in such a form where we have some clauses, ors in between, and they're all clauses, and then an ands in between. This is one of the standard forms, which is very easy to see. Let's say if it's correct, that all of them need to be correct, and so on. So it's a nice form, but to just take a formula and put it in the correct form, it's hard. We need an exponential amount of work. And this one here. Well, this is from XKCD, but it's really funny. So it's a traveling salesman problem. You've probably heard of it. So the salesman needs to go through all the cities to sell his maybe vacuum cleaners, let's say, but he doesn't want to walk an unnecessary path, so doesn't want to go through a city twice and wants to go through all cities. Well, it's a really hard problem. If we brute force it, we have n factorial, which is a lot. Some better algorithms say that it's worse than exponential. Yeah, online shopping faster, but yeah. So it's a hard problem. So today's cryptography uses hard problems. It doesn't use any of these. I forgot to tell you this. If perhaps some of you doesn't have mathematical background, this is a nice graph to see what is the difference between the most important complexity classes. So ideally, we would want to base our cryptography on a hard problem, let's say here somewhere, or maybe, yeah, here somewhere, but also needs to be more difficult than polynomial time. We consider polynomial time efficient. Like if it's n to the power of 20, that's not really efficient, but in mathematical terms, it is. Today, we use mostly, like all that I said previously, and the most widely used are the problems based on integer factorization and discrete logarithm. So what is integer factorization? It's very simple. If we are given one very big number, let's say 2048 bits, we want to find its prime factors. Usually, it will only have 2 prime factors. That's the point. This problem is difficult, but is not as difficult as exponential running time. It has a sub-exponential complexity, but still that's bigger than any polynomial complexity. Still good enough for us. The other is discrete logarithm. We all know logarithms, but that's with the real numbers. So we had those tables. Nowadays, kids don't have them because they have calculators for this. Yeah, but we had those tables to read the logarithm of a number. But that's for real numbers. We can't do it if the numbers are integers or they're in some group. So it's also a hard problem. But these two are very much connected. So as I said, sub-exponential complexity, lower than exponential, but higher than polynomial. So these are the standards now. Okay, that was crypto. Now let's see the other party in our battle here, quantum computers. Well, they originate far, far back from the ideas of Turing. So the Turing machine is an abstract thing that says any algorithm can be efficiently implemented on this Turing machine. So that was in 36, and Gilles in 77 said that, well, the first concept did not include probabilistic algorithms. And then he extended this, and there came the probabilistic Turing machine. And it looks, let's say, something like this. Here's the infinite stripe, let's say. And this machine can simulate any algorithm. So this was the beginning of computers, because we knew that whatever algorithm we think of can be simulated on this one and can be implemented on a computer. But then Feynman in 1982 asked a question. Well, what if we have some physical system and some quantum phenomena? Can they be simulated on some sort of a machine? Well, they can't be simulated on a probabilistic Turing machine. But if that's not the case, can there be some machine on which this can be simulated? And that was like, in general, some physical system. And there came the universal quantum computer defined by Deutsch. So the universal quantum computer is the same concept, not the same concept, but of the same type as the probabilistic Turing machine. This one, that's why it's called universal, would be able to simulate any physical phenomena. Why is this important? Because nowadays you may hear on the news or something, computers that claim, I don't know, 500 qubits or something. That's the D-wave computer, but that's not a universal quantum computer. That can do only some operation, and it's still not known whether actually it's faster than a quantum computer, but faster than a classical. But even if it is, it can't do any. So the universal is like our pieces. You can do everything. And here's maybe a depiction of what this might look. This is not a mistake. Actually, that's because we don't have a universal quantum computer. We are almost there, but no, we don't have it. Why almost there? Well, the past few years have been very nice for the implementation of quantum computers. There are some problems still, like the quantum computers require very low temperature. Otherwise, the qubits will be influenced by the environment very easily, and that quickly, the state quickly disintegrates, let's say. So there are problems, but I'm not a physicist, so I don't know the details, but however, there is progress. So IBM is probably the company that invests the most. $3 billion they invested in this matter. So, yeah, we can expect something. So I mentioned this earlier. So they're already there. 50 qubit computers. Also, Microsoft is working on a different type of computers, but they're called topological computers, but they need the existence of a particle that has not yet been proven, but on the other hand, doesn't have problems with the errors. Yeah, so some may think this is crazy to do this, but on the other hand, it's a plausible thing. So, yeah, can be done. So here are the various quantum projects with different technology and what might be the problems with these computers. Okay, so let's let's peek into a quantum computer, even if it's not there. The math actually is very nice. So quantum computation is a very beautiful kind of linear algebra that describes what would happen in a quantum computer. The bits are the unit of classical information. There is either 0 or 1. We can put in 1 bit, we can put this much information, tell yes or no. Qubits, well, that's the unit of quantum information. It's not 0 or 1, but it's kind of a combination of 0 and 1. Actually, a linear combination of 0 and 1. So think of the 0 and 1, 2 vectors of length, of unit length, and think of a linear combination of these. So very easy to describe. It's just a vector. An important thing in quantum computing is that of measurement. What we have here actually kind of describes what are the odds of getting a 0 or 1 when we measure this qubit. So the probability that the outcome will be 0 is alpha squared, and the probability that it's 1 is beta squared. So the measurement is non-deterministic, and we don't know exactly what will happen, but we do have the probability of something happening. What is important? Just as the Shannon theorem says that we can't, there is a bound on what the information is, a bit is a bit. Here, even though it may be counterintuitive, the amount of information you can put in a qubit is also 1 bit of information. It's a bit strange, but that's the case. What is there in a quantum computer? Quantum gates. As in a classical computer, here we have also gates. But what is important about quantum gates is that they are unitary operations. What does this mean? This means that they are reversible, which is not the case in classical gates. So if we have, for example, classically AND gate in a computer. So A and B. When we get the result, there is no way back to come back and see what A and B were. So that's not doable classically. But in order to preserve the principles of quantum mechanics, this has to be the case. So all gates are represented as unitary operations. So there are one qubit gates that act on a single qubit. Oops.
So,
and two.
so does that mean that probability is kept same if you do such a unitary operation? Total probability has to stay 1.
Yes, it is always the total probability.
The operation probably has to be unitary.
Yes. So it will preserve this. So these are the unitary. Let's think of it like some linear transformation. So these will always be preserved. So that's the point. So for example, let's say this X, Z, and the Hadamard gate. They act on single qubits, and if, for example, this is a representation of a qubit, through this gate we will get this one, and this is kind of, think of it as the NOT gate classically. So if we start with a 0, we end up with a 1. So if we only have this one, then we end up only with this one. So here, the Z1 kind of changes the sign here, and this one is kind of like a square root of a NOT gate. So very useful one we will see later. We can have 2 qubit gates or several qubit gates. So here, what this one does is a controlled NOT gate, and depending on this A here, we will have NOT or no NOT. So that's why controlled. So what kind of computations can we do in a quantum computer? So can we do classical computations? So this is very important. If we can't do classical, like this, it will be really difficult to think of algorithms that can be done. Luckily, it is possible. Actually, we can simulate entirely what's happening on a classical computer using a quantum computer, and this kind of makes sense. For example, if we have this gate called the Toffoli gate, if we input A, B, and 1, the result that we get here is a NAND gate. And we know that classical computers, everything on a classical computer can be represented by a NAND gate because it's a universal set of gates, only a NAND gate. So that's enough to show us that everything on a classical computer can be done here. Also, if we, for example, do this, get the 0 through a Hadamard gate and then measure, then we will get as an outcome either 0 or 1 with probability 1/2. And we can think of this as a random coin tossing. So anything probabilistic can be done using this one. So this means we can efficiently simulate a classical computer. Why bother do this? Like, I mean, we have classical computers and they're really good. We know how to put like tremendously dense chips on a silicon, on an atomic level, and that's extremely cheap. So there must be something else. The first thing is quantum parallelism. Think of this problem. Evaluate a sum function for many different values of x simultaneously. So this would be the gate. This u is some unitary gate. And we have some x and y here, and in the end, this is the result. So if we have as an input 0, 0 here, in the end, here we will get 0, f of 0. So here will be f of 0. If we have this input, here we will have f of 1. But this is just to find out what f of 0 is and f of 1. How can we do this simultaneously? Well, if this is the input, it's not hard to see that the output will be this one. So somehow we have f of 0 and f of 1 here. So one operation, so just going through this gate, we calculated both f of 0 and f of 1. Yeah, let's stop here. This doesn't mean that we can see both. Yeah? If we measure, we will only see this one or this one. So it's not as easy.
Is this what Deutsch used to prove that quantum computers would be faster than?
Yes, he used this. The problem, I will come back in a slide or so. The problem is about whether a function is balanced or not. Yeah, it's the next slide. So that's the Deutsch's problem. So very simple one, 0, 1 to 0, 1. So a function, if it's balanced, then the result is for one value is 0, for the other value is 1. Doesn't matter which one. If it's constant, for the both values, it is 0. We can't really extract both. It will be it's against the principles of quantum mechanics that we can see both f of 0 and f of 1 at the same time. But for example, this problem exactly shows that it's faster on a quantum computer. Imagine you want to do this classically to test whether the function is constant or balanced. So you need to see f of 0, let's say it's 1. This doesn't tell anything. Like, we have one computation which doesn't give any information. Only the second computation can tell us whether it's constant or balanced. But let's go back here. What if we somehow can add from this one, so make some transformation that ends up in adding f of 0 and f of 1? Then if we have a constant function, this will always be 0. If we have a balanced function, this will always be 1. So if we can manage to add this somehow, which that was what Deutsch did, in some transformation, I will not show that, but if you want, in the end, I can find it. That's what Deutsch did, and show that it can be done in one measurement. So that was the first thing that Deutsch did. So this is called interference, like taking both things and interfere them together. And these are the algorithms, let's say, that led to Shor's algorithm. Actually, today, scientists have found many other applications of Simon's algorithm, but this was only like 2 years or 3 years ago that they found applications of Simon's algorithm in cryptography to break stuff in crypto. And this one was before Shor. And then came Shor. Actually, Shor was inspired by Simon. It's a period finding algorithm. And Shor's algorithm is also period finding algorithm, but he knew very well number theory to understand that factoring is equivalent to period finding. And then came Grover's algorithm. Shor's algorithm combines number theory, quantum parallelism, and quantum interference to get the result. And the best classical algorithm is the general number field, see if it has a sub-exponential complexity. But yeah, there have been improvements of this one, but not escaping this one, no polynomial time complexity. Shor's algorithm has cubic complexity. So this is what I showed earlier. That's a very big difference. And Grover's algorithm solves the search problem. Find an element in a non-sorted, let's say, database that satisfies a given property. It's an algorithm based, it's a completely different algorithm. So this is an amplitude amplification, this algorithm. It's a very different concept than Shor's algorithm. And it's a quadratic speedup. So everything can be done in square root of the size of the database. We already saw this little example. So, yeah, an important thing is that it has been shown that this is the best thing. So we can't have bigger than quadratic speedup with Grover's algorithm. So not with with any algorithm for the search problem. So it has been shown that this is optimal. So this we will see later. This kind of says a lot about the power of quantum algorithms. They're not all powerful. So even though we don't have proofs for that yet. The quantum computer, well, probably will eat our crypto. So these are the algorithms that we use today. Elliptic curve cryptography, you've probably heard of that as well. Diffie-Hellman key exchange, the RSA encryption scheme. And I mentioned previously what the impact is on all protocols that are secure protocols. This will have an effect. But also on things like electronic voting, digital cash, bitcoins. Like that's a big hype. There's a big hype with those now. So everything will be affected. So some numbers. These are what we use today. So for example, for 80-bit security, which is now considered very low, it's not enough, but we say that if something offers 128 bits of security, that's enough. For example, elliptic curve cryptography 256 offers this security. But of course, no security with quantum computers. Regarding Grover algorithms, block ciphers, that was the first idea Alice and Bob had with symmetric crypto. Stream ciphers as well, hash functions, that's used everywhere, like to check the validity of a document. First, in hash and sign signatures, almost everywhere. But also primitives based on NP hard problems. So we just don't use any smart algorithm, we just search, but we have a quadratic speedup over a brute force search, which is quite significant. Here, there is a difference, but it's manageable. So 128 bits of security, this means it will take 2 to the 128 operations on a classical computer, but that's not insignificant on a quantum computer. Let's say for this one, 2 to the 64, that's not a lot, but 2 to the 128, that's a lot even for a quantum computer. So kind of manageable. Emerging questions. Well, I would ask, of course anyone would ask, so is it possible that actually we just don't know a better algorithm for RSA, let's say, or for integer factorization? Okay, I mean, we are humans and we make discoveries. Isn't it possible that after some time we will just discover, let's say, a classical algorithm for integer factorization and discrete log? Also, what if, but I already told you, what if there are other algorithms like Shor's algorithm that break other primitives like, let's say, MP hard problems? I already mentioned this. Well, the thing is, like for some of these questions, nobody knows. But there are implications. But actually, we don't know the actual complexity hierarchy that we have, how do classical and quantum algorithms and how complexity classes interfere. Here's a nice picture. So this is the alphabet soup that we know of complexity classes. We have the complexity class P. Those are deterministic algorithms, solvable in deterministic time. And we have MP class, that's algorithms such that the solution can be checked in deterministic time, polynomial deterministic time. We have P space, like they are solvable in polynomial space. And we have these two important classes, BPP, solvable in polynomial time with bounded probability error, and this one using a quantum computer, the same one but using a quantum computer. What we see here is what we know. We know that BPP is inside BQP, and we know that P is inside NP, and they're all in P space. Of course, you know all that. We don't know what's the relation between P and MP. We know that probably they're not the same, but we have no proof. Similarly to what is the connection to BQP and BPP. So what is this one and what is the connection to NP? So we can take a look at like two cases, extreme cases. The first one is that BPP and BQP are the same. This would mean that our class that we can solve stuff on a classical computer is the same as what we can solve on quantum computers. So we can just forget about the 3 billions of IBM and just work on classical algorithms. That's all we need, right? This is very unlikely that that's the case, but yeah. The other extreme is that this NP is inside BQP. So everything can be solved in polynomial time on a quantum computer. All are NP hard problems. This is also very unlikely. And if this actually happens, then classical cryptography or whatever classical, whatever security based on classical assumptions is gone. That's it. Both are very unlikely, and what I mentioned about the optimality of Grover's algorithm kind of implies this, because the Grover algorithm is the best algorithm to search for a solution of an NP hard problem, and so this kind of implies. It doesn't prove anything. Yeah. So kind of AES and such algorithms are safe, but RSA is definitely dead. Discrete logarithm is definitely dead. But we saw at the beginning that public key cryptography is very important. Otherwise, it will be difficult for Alice and Bob to share the key. So it is important to solve this problem. Perhaps we can use quantum cryptography. We had an earlier chat before that maybe we can just use quantum phenomena to do all this. But another alternative is to actually have strong cryptography that will be secure in a world with quantum computers. This might, like the strong classical cryptography from what we saw until now, it kind of implies that should be either based on some of these symmetric primitives that we saw or maybe on NP hard problems. So we are going that way. So quantum cryptography, well, uses quantum phenomena and would need machines that are able to demonstrate these quantum phenomena. And there are many things that can be done. So quantum key distribution has already been done. The Chinese have sent a satellite in space that does quantum key distribution. Quantum random number generator is very easy to make. We just prepare a state such that we have an equal probability in the end, then measure, and we are done. Quantum commitment, we can commit to values using quantum effects, quantum money, quantum e-voting, and so on. So all these have been done theoretically, so we know how to do this. The point is, who will be able to use this if we have the technology? Very unlikely that we will be used as normal people, like everyday Joes, to use these types of, let's say, crypto primitives. Probably just to governments and big corporations. A better alternative is post-quantum crypto, which means that post-quantum crypto was like the term maybe a little bit misleading. It kind of usually we have some like we have classicism and then neoclassicism or post something, but we don't need quantum cryptography to get up to post-quantum cryptography. That's the point. We saw this earlier. Post-quantum cryptography is such that Alice and Bob are classical, and Malice is quantum. And she has the quantum computer, and Alice and Bob still want to communicate securely. So all algorithms like this are post-quantum cryptography. So nowadays, these are the algorithms that we know of that are post-quantum cryptography. I wouldn't get into details on what these mean, but I'm sure you're very much interested what kind of systems these are that are secure against quantum computers. So I will show the one that is probably the easiest to get a global or big picture of. So those are code-based crypto systems. And as a matter of fact, they're not invented like yesterday or something. Like Michaelis's crypto system exists since 1978, the same year when RSA was invented. So it's as old as RSA. And you might ask, why is RSA used and not Michaelis? Well, for efficiency reasons. Michaelis has huge keys, whereas RSA are counted in bits. So in order for this to work, like, who cares about security if it's not usable, right? If the system is not usable, then, So it has to be both secure and usable. So Michaelis's scheme is based on something that we know from telecommunication. So we have two parties. They don't want to hide their communication. They just want to transfer their communication without errors. Imagine the satellite, or I don't know, some Voyager sends images to Earth. So much noise, and it has to be somehow like the noise will interfere with what is sent. In the end, we have to be able to reconstruct the picture. So the encoder encodes the message, and in order, so this is true. This holds because of Shannon's theory. So we can't expect to send just these k bits and error to occur and then to be able to recover the previous. That's impossible. So we need to add some more bits to this. So this encoder somehow encodes the message, and the message becomes longer, but it doesn't matter. In the end, we can go back and recover the original messages. So the channel introduces some errors, we say. And how is this used in cryptography? Well, imagine that Alice puts this error onto the message after being encoded on purpose. So that is how the system works. So Alice has this message, encodes it, and puts some errors. So intentionally puts this. At the other end, Bob has some decoder such that he finds this X. It turns out, for specific encoders and decoders, if someone sees the ciphertext with this additional error, it's not possible to go back. Or at least it's not possible in efficient time. So this is how it works. And it's based on an it's proven that it's an NP-hard problem to decode a random linear code. So given this and knowing how the encoder works, to go back to find what the message is. So this is a hard problem, and works this way. So it's a simple idea, and it works very well. There are other systems like multivariate quadratic systems. This is actually the area that I work in the most, and it's based on also an NP-hard problem, solving systems of equations, but not linear equations, but of higher degree. So we know that if we have a system of linear equations, it's easy to solve it. Like we need at most cubic amount of time, Gaussian elimination, and we're done. But if we just increase the degree to 2, it all of a sudden becomes an NP-hard problem. Best things to do with such systems are signatures. There are also lattice-based systems, many different types of errors here. You can think, problems here. You can think of it as similar as the code-based system, except that the errors have a Euclidean norm, and these have Hamming norm in code-based systems. Hash-based system, they're based on hash functions. Also very old idea from 89. Isogeny-based systems, very new idea. And kind of we don't really know how hard it is still. We think it's hard, but we don't know. And there are quite a few challenges in this area, in post-quantum crypto. First of all, let me tell you that even though the systems are not very new, the area of post-quantum crypto is quite new. And as we have problems with figuring out how algorithms on quantum computers would work, we would have problems here, because we need to place our parties in a quantum world. So the adversary has a quantum computer. So there are problems in how to model these adversaries. Like they will have a quantum computer, but we still don't have a quantum computer. This is very difficult to say like this is a good enough model. The model that we have here classically are because we look from practice, we see what makes sense, and we model this. So we may overshoot the model and obtain nothing, or make a very weak model. How to prove that something is secure? It turns out that the techniques in the security proofs, so in the math proofs that we use, will not apply on quantum computers. So with quantum adversaries. So most of the techniques used do not apply. So now we are in a process of thinking of different types of techniques to prove security. And also, as we saw on the previous slide, are these problems really hard? Can we make other algorithms where we use Grover in a more smart way than just brute forcing and so on? So new algorithms and so on. How many qubits will these algorithms need? Yeah. Thank you. The key sizes and the speed are an issue. Just as an example, ECC 256 key is 256 bits, only 256 bits. Whereas McAleese's keys, or the public key, is 500 kilobytes. Like it's even incomparable. Like ECC, the size of the signature is 80 bytes. MQDSS, 40 kilobytes signature, 40 kilobytes. Like imagine in each and every establishment, like when you browse, each and every connection to a server needs this, and like this is a huge jump. Also, these are the classical algorithms that we have now, are all well implemented on all those servers. So you can go on the internet and see a very good reference one. And if you're a programmer, you can find one and so on and use it on your system. And which algorithm to use? We have no idea yet. Well, we have, I mentioned earlier, we have a standardization process. And then this needs to be deployed, and it takes a lot of time. So I mentioned the NIST competition and the timeline. Yeah, we're somewhere at the beginning still. It's not a competition, that's what NIST says, and that's a good thing in a way, in the sense that in the end there will be several algorithms that will be chosen to be used, not only one, which is kind of good with the cryptographic principle of not putting all your eggs in one basket. Yeah? So to have alternatives. Yeah. And these are the ones that Radboud is involved in. Yeah, you can quickly read their names. I hope that some of them will be in the final portfolio and be part of the standard. And the one that I'm involved in is this one. It's a MQ signature that is actually the first that has been proven secure. So that was it for my talk. I hope you enjoyed it, and thank you. And I like these quotes. I almost always end up with the quotes about quantum computers. And if you have some questions, please. Yeah.
I have a question already from the beginning. When you encrypt a message with a key, and someone tries to decrypt that message, he will have to find the appropriate key to do that.
Yes.
But how does he know that he has the correct key? If he gets out, he can wait until he gets out some sensible message, but is that the message you want to have? In order for the communication to be to go smoothly, we usually don't wait for the entire message to come to decrypt it with a key. So this works on blocks. So I know that I have a key called the session key usually. That is the communication between me and that server, for example, for this particular session. And then the key has been established like a second before or something like that. And we use it in this session. And that will be the key. We know both that that will be the key. And in the process of this key establishment, we also authenticate whether I am the right person, that's the server, or just the server authenticates to me. And afterwards, we assume that that's the key, and that's the key that is being used. And it's used on blocks, like on 256 bits. So when the first 256-bit block arrives, I decrypt it with that key, and then the second, and so on. Yeah. Did I then misunderstand that what you have to do is find the appropriate key without knowing anything about the first thing?
No. The key is used.
Yes, yes. So the key is not the message, and that's used for the entire session. So in
Also, you don't encrypt the message itself with the key, but you only encrypt the whole of the message with the key.
no, the message is, for example, the message is, let's say, how is this done?
It's automatic. Because
Ah.
turning the bar. The bar.
This one?
Yeah.
Yeah.
How do I turn it?
Either way.
Ah, nice.
That encryption was easy.
So for example, if we have this message, let's say M1, and then the message is split into blocks, M2. There are different ways of doing this, but let's say a simple one. So this message goes into some like encryption algorithm, and here we use the key and the message together, and something is done here, and this in the end spits some ciphertext 1, and this is then transmitted, let's say. And for example, for the second block, it is possible to do exactly this thing, or for example, use this one here to make it a little bit more complicated, but that's not interesting at the point. But the second, let's imagine that the second one is also done the same way using exactly the same key. And yeah, again, the same thing. And here also this key, yeah. Again, the same key goes here. And so on. And when the other party wants to decrypt, has exactly the same key, and starts from here, and has some decryption algorithm, inputs the key there, and spits the first message, and then the second message, and so on. Yeah. So it's not that simple usually, because this kind of leaks some information, this way of encrypting. But it's not important
But when
here.
you try to break in on this,
Yes, I would.
you try to find out what key is used.
Yes, and I brute force it. Brute force it and do
But
this.
how do you know? The only way to check whether you have the correct key is to see if you have a readable message and one.
Yeah. So that's.
And how are
that.
you sure that that's the correct message?
Yeah. Well, you're not sure, but if all the messages make sense, it's very,
That's
very,
the way of doing it.
very, very
You
probable
break
that.
up your messages in single words and send it separately.
Yeah. So usually how you would break something, if you know, for example, if the algorithm kind of allows, for example, if I know the first message,
Yeah.
it's always "Hello, dear," and I can use that knowledge. I can see what the ciphertext is because I can observe it, and I can try using that to find out what the key is.
So you need additional knowledge.
Well, depending on the algorithm. Some algorithms are weak, and then you would just like break it without additional knowledge. But the ones that we use are not breakable, even if you know what the message is. So AES is secure, even given that. Yeah. So that's the point. We assume classically that the adversary has all the power in the world, in the sense that he can lie to the let's say to the encryption algorithm or the decryption algorithm. He can feed, for example, the algorithm with messages and see what the output is. So we assume all that is doable.
These are additional methods, but what
Yes.
they wanted to know how can you be sure of the first step?
Yeah, that would be the case. Yes. Anything?
How far away do you think it is when we really meet a quantum computer?
A universal quantum computer, that's what we need for these problems. Well, I would say 15 years. 15 years.
Can artificial intelligence help us to speed it up?
Don't think so.
Why not?
I mean, it's an implementation thing. Like, we need to figure out how to make the computers, right? So how to deal with the decoherence and make it work on a room temperature. How to, Yeah, technical. Yeah. The theory is there. Some of the theory is not done, I suppose, but we need to test. Like, we test our algorithms on computers all the time.
And the 50-bit IBM computer, is that already universal?
Yes, it is, but it's 50 qubits that are physical qubits and not logical qubits. And there is a difference here because of the decoherence. In order for any of these algorithms to actually work, you need to kind of double, for each operation, you need more or less to double the amount of qubits that you have. So, and work on the logical. So, for example, in order to break RSA, you need, if I'm not mistaken, like times 4,000 or 4 million, something like that. 4 times 4,000 qubits than the amount that the algorithm says, because of the decoherence and stuff like that. So that's the thing. So when the physicists figure out how to do this better, then I think this will approach the physical will approach the logical, but never be the same. The amount of qubits needed. But for example, the Shor's algorithm has been demonstrated for 21, to factor 21.
Are you almost ready?
We're ready. We're having questions. Yeah.
Okay.
So it has been demonstrated that it works. So on 21, it's a small number, but yeah.
I'm not sure what it was, but I once heard something about sending a message in terms of qubits. That would be its final solution. But you think that's possible in the future?
Why not? Yeah, why not? Yes.
Then you can see whether it's read out or not.
Yes. So, for example, quantum key distribution, you can be sure that no one saw what you sent, because if it was intercepted, then it was the state was destroyed. I did my PhD in Norway, and then there was this the lab, the quantum lab. They broke several commercial random generators that do this, like send, and you're sure that what the key that is generated, blah blah, is not intercepted. But they managed. I don't know how they did it, but I'm not an expert. But they managed to break the actual implementation. So it means that commercially, even though they claim that this can be done using lasers and stuff, something was wrong, and the commercial products did not actually do what they promised. So I would see the problem there, because we would all need to use something like that, and it will need to be cheap and reliable.
Yeah, one question is, if you look at quantum states, and you can have superposition in states, it might be that if you put a problem into the quantum computer, and then you have all kind of quantum gates there, like the Hadamard you mentioned, and then of course there might be an outcome, but that outcome, as soon as you read it out, it might be such that it has certain probabilities, the outcome, and that it might be that the real outcome might be a probable solution, but maybe not the final solution. How do you deal with that? Because if you measure the quantum state, also in physics, because I'm a physicist, then you can always have more answers. There are probabilities that you get a certain answer if you measure. So if something comes out of a common computer, what comes out will have a certain probability.
So
you never have a deterministic answer. How do we deal with that?
So for example, I will show you. I have it here somewhere.
The probability is what? You know.
Ja, maar soms is het makkelijk om het antwoord te checken. Dan kan je het natuurlijk checken.
Okay, so Grover's algorithm, for example, it's a very, we can see how it works very nicely on a picture. So we start with some, let's say, we split the set of solutions here and the set of non-solutions here, let's say. And we can, for example, for a problem, when searching a database, what would be a solution? The one that satisfied what we are looking for. For example, we are looking for a, I don't know, red house. Yeah, and if we know that the solution space has a number of red houses, we can say that this has this many. And here, this one, for example, actually. I will not go into details how this one works, but starting from here, the algorithm is such that after a number of steps, what the outcome is, like we can do steps and measure, like once, twice, iterate several times. And we can show that after a certain number of steps, the solution goes closer and closer to here. And when we measure, the probability is the highest that we will get the solution. And still it's... Yes, for this one. Yeah. So, for example, if we measure the first time, it will be very far. So think of the previous picture at the beginning. So this one is a linear combination of these two. So this S here. So in this case, this is much closer to the non-solution. So if we measure at the beginning, yeah, we won't get it. And for Grover's algorithm, as the algorithm progresses, so first it makes a picture here and then here, and in each iteration, this is what is done. So across, then the second one will be across the x-axis, and then across this one, and so on. And this amplitude for the second one, this one, like this is the qubit, let's say, or the state. And this is the first probability for non-solutions and the second for solutions. And as the algorithm progresses, this one grows, this one gets down. But the point is, okay. The point is, you can see from the picture, like if I continue, I can overshoot. I can go over it and then maybe get to the non-solutions again. So it actually, you need to perform exactly this many rounds or approximately this many rounds to get the highest probability of the solution. And if you do it more, then again, yes.
Or you could use a classical computer in case that checking the
Yes.
outcome is easier
Yes.
than to compute the outcome.
Yes, because NP-hard problems are the ones that you can check in polynomial time the outcome, and then you can check whether this is a right solution. Yes. Yeah. But still, it can be tuned when to get a better one. Yeah. Any more questions? Well, thank you.